Hey there everyone, this is Shivani with GoEngineer. This is going to be a webinar about how to use porous media. We'll be going over the assumptions and methods you need to know when creating a custom porous material. And then we'll use that to test some complex geometry. And we'll be replacing the complex geometry with the porous media block instead. We'll see how to properly do that. So let's start by setting up a basic example, this porous media catalytic converter right here. In Flow Simulation and other CFD packages, we're generally solving for the conservation of mass, momentum, and energy using the Navier-Stokes equations. And one of the main parts of the Navier-Stokes equation is the change in pressure, or the pressure itself. But CFD doesn't have a way to calculate the change in pressure across a screen or a filter. And that's why they started using this porous media instead. What porous media does is use a pressure drop versus a flow rate that we tell the software. So we tell it what we expect the pressure drop to be, and it just pulls that data from a chart. So that's how it's able to simplify that. Let's go over the basic setup here. My general settings, I've got an internal flow for this catalytic converter, and I'm using air running through from the inlet face here to the outlet. Everything else is on default. I've got an adiabatic wall. My initial conditions are default as well. My inlet velocity is about 39 feet per second, and my outlet pressure is atmospheric. Now I need to set up these solid blocks as a porous media itself. So I don't see that in my tree. The way you add different types of tools to your tree is to right-click your setup, go to Customize Tree, and you'll see a checkbox or a choice for porous media. So that pulls this in here. I'll right-click, insert porous media, and I'll choose one of my solid components. Now, SOLIDWORKS comes with a few defined types. I'll stick with Isotropic for this first example. What Isotropic does is assume the porous media's porosity is the same in all directions. The pressure drop will be the same in all directions. So I can click OK. I see my three arrows here talking about the isotropic. If I take a look at my component control, we'll see that the two solid blocks that I chose for the porous media have been unchecked. This means that fluid can now flow through them, whereas before they would have stopped the flow. Now if I went ahead and ran this, we would be looking at results like this. So as the flow starts to move through these porous media blocks, it's forced to straighten out and slow down. So you do see a sort of pressure drop. We can actually take a look at these XY plots. So the pressure at the beginning is much different from the pressure at the end. You do see that pressure drop. So take a look at the isotropic look of this. You can see that these lines are slanted. As a comparison, I'll show you the unidirectional plots as well. And you'll see that the unidirectional flow trajectories are much straighter through here. They're forced to run in a single direction instead of being able to run in all three. Now it's nice to have these two different types and to have these different materials that we set up here in my setup. However, I wouldn't always be able to use these types of materials for a real analysis. I would have to be changing the material type if I wanted different pressure drops. I can't always be relying on changing the length or size of my porous media. So I do have to create these myself. How do we do that? We'll take a look at the engineering database associated with these porous media types. Starting with the isotropic, if we look at the item properties, we see that it's defined as a pressure drop versus flow rate. And looking at this table, someone's imported just 2 data points and created a linear curve. So if SOLIDWORKS sees a particular pressure or velocity at the inlet face of the porous media, it pulls the other piece of data and continues on with this calculation that way. So it's really and truly just reading data straight from this chart. Now, 2 data points is not really enough data to be trusting this material anyway, so we definitely need to be making one for ourselves. So let's go ahead and do that. I will come over here to user defined, and we'll look at this one I set up for the catalyst study. And this allows me to start changing things in here. Starting from the top, a porosity is how much of the fluid is flowing through the porous media block. So if I set this to 0.5, that means 50% of this volume is actually fluid flowing through it. For these permeability types, isotropic means it's going to be the same in all directions. We also have a unidirectional, which is only the x direction will have any flow, the rest will be nothing. Axisymmetrical you can use if you have round filters, and orthotropic if you have different flow rates in different directions, different pressure drops in different directions. This is the most general type, and if you were going to be creating your own custom material, most likely orthotropic is the one you would be using, because that's the one that's going to be most accurate. But we'll stick with isotropic for now, and we'll take a look at the resistance calculation formula. So when we were looking at it earlier, the predefined isotropic was using pressure drop versus flow rate. And if you were measuring data in your lab, this is the one most likely you would have. It would be the easiest to import. You would be copying and pasting straight from Excel into this chart right here. We also have this dependency on velocity type, and we'll be going into how to use this one. You can get this data directly from the pressure drop versus velocity chart. And it's a little bit more requires a little bit of data changing, but it will actually get us more data points than just using the couple or few that you would have created in your lab. So hopefully you have a lot. If you don't have a lot, then you can use dependency on velocity. These other 2 types, dependency on reference pore size and this with Reynolds number, these are best used if you guys have vein bundles or you have long thin pipes in a flow. The pore size is talking about the cross-sectional area of one of those veins, of one of those cross-sectional pipes. You want to be using dependency on reference pore size if you have, if you're going to be assuming laminar flow through those pipes. If you want to also calculate turbulent flow, then you need to use this last choice. Now all these different choices, they're actually pulling in information from this A and B right here, or as I'm going into pressure drop, you'll see length and area. So whatever data points that I'm putting in here is calculating a certain constant, and this constant is called K. And I've created some equations for you to look at here. The standard equation for K, it's used in a force calculation that goes back into the Navier-Stokes equation. And there's lots of different equations for K, different ones for the different types. The dependency on velocity type has an equation like this. The other choices that we looked at, the pressure drop versus flow rate, you see a K value created from this equation here. And this will be for the reference pore size, and this is the reference pore size with Reynolds number. And you can get all of this data from the Flow Simulations Technical Reference PDF that comes with your installation. Okay, let me go ahead and set this up to the dependency on velocity type. This is the one we're going to be looking at together as we create our own custom material block. Now, I don't have a lab to test these material blocks in, so I'm going to have to do a flow simulation wind tunnel setup instead. This is what you would want to do in real life, and if you really just didn't have a choice, then you could do it inside of Flow, the way I'm about to show you. So let me go ahead and close this. Open up my wind tunnel model, and we'll be turning this grate into a porous media block. So we'll be determining the pressure drop across this grate for different velocities, creating a pressure drop versus velocity curve, and then transforming that into data points that I can put into the dependency and velocity choice inside of my porous media. Now this isn't very complex. That's going to make my simulations run much faster. You could do this for much more complex geometry. All you really need to find out is a pressure drop across that surface. So to set up the wind tunnel model inside of SOLIDWORKS, let's see the choices that I need to make for this. On my general settings, again, I'm just doing internal. For fluids, I'm going to be using water for this analysis. On my walls, the default wall will be adiabatic, but you'll see that I changed this. And my initial conditions are also a default. I've got a velocity in the z direction set a little bit higher than 0. This just makes my calculation run faster. The initial conditions here in the general settings, this is just where the solver will begin calculating as it tries to find equilibrium. So setting this higher actually makes my calculation speed run faster. Now for the setup here, I've got an inlet velocity of 0.1, and I do change that for all these different projects. Got a static pressure at the outlet, 101,325 pascals. And for the 4 walls of my wind tunnel, I've created an ideal wall boundary condition. Now the only goal I've set up is a surface goal. It's an average total pressure on the inlet. This is useful information, but I'll tell you why this can lead you astray as we move forward. So you would run this. It took me about a minute to run, actually. It's a pretty simplistic model. And I was able to create this XY plot. It's following this sketch line right here. I'm able to see the pressure drop from the beginning to the end of my wind tunnel. A little bit hard to calculate there, so that's why I would go into my surface goal instead. That's my goal plot. And I would see that the pressure at the inlet is 101,342. So I could use this value, use my outlet value, and find the pressure drop that way. Now, that's actually one of the biggest mistakes someone could make, because you're assuming that the pressure drop is what that you care about is from the inlet to the outlet, which is not true. The pressure drop you care about is from the inlet face of the porous media block itself. So not the one over here, but this one here. So instead of using this goal plot, I'm going to be using a surface parameter that I created at this face. I'll go look at the pressure. So the 101,339 pascals is what I need to be using for my pressure drop versus velocity curve. So let's go ahead and take that number. Let's put it into my Excel sheet, 101,339. For the 0.1 meters per second velocity calculation. I'm seeing a pressure drop of 14 pascals. And I'm unable to get a pressure gradient yet because I need to be dividing by the characteristic length. The characteristic length, you can see this equation right here, is the thickness of my porous media block. So this is going to be the length of the block that you test in your wind tunnel, or the length of the porous media piece that you want to set up later on. It's not absolutely necessary that you choose the exact thickness of this block, because for SOLIDWORKS to be accurate when you're creating porous media, when you're using the porous media choice, you want to at least have 5 to 10 cells across its thickness. With thin parts like this, having 5 to 10 cells can really amp up your mesh. It can make the solve time much longer. So if you actually make the porous media block a little bit wider, you'll still get the same results in the end, and it'll be easier to mesh. It'll run faster. Going back to my XY plot, I'm going to use this to figure out what length I should make the porous media block. I don't have to make it the thickness of this porous media. So looking at this jump, I would say the porous media block starts at about this value and ends maybe right around here. I could extend it further. When I put in the pressure drop, it's going to be between this value here and this value here. So this is really the zone that I'm going to be creating with my table. All of this data will be lost. I'm going to say that my pressure drop occurs between here and here. That's about 0.018 millimeters, or 0.018 meters. I'll go ahead and put that into my table. And that's created my very first pressure gradient. Now I've gone through and I've done all these for the other velocities, so we won't need to sit here and do that. So I'll copy those over. I ran this for 0.5 meters per second, 2 meters per second, 3.5 meters per second, and 5 meters per second. I was able to determine these pressure gradients, and I'm starting to see a curve getting created here. It's a parabolic curve. I know that because of a side equation that we need to calculate. From that technical reference, I see that the resistance term, the resistance coefficient, is represented by this, the AV plus B over density. A and B are coefficients that we get from this curve. If I set this equal to the resistance to fluid flow equation, I'm able to get this quadratic equation down here, where I'm equating the pressure gradient to a quadratic equation, which is this plot right here. So if I begin to use the trend line inside of Excel, set this up with a polynomial with an order of 2, and ensure that my intercept is at 0. Let's do these two. I can create an equation that tells me A and B for the dependency on velocity inputs. Alright, now that I've got A and B, I need to take a look at that R squared value. This is a statistical number. It tells me how close my trend line is to matching up with the points. A number of 1 is exactly matching up with all of the data points. So that's pretty idealized. Obviously it's idealized because I'm using flow simulation, because I'm using a very coarse mesh. My inlet pressures are rounded off instead of to decimal places. In real life, you just want to get a best fit curve, hopefully above 0.9. That way you can calibrate your results. So let's go and take these numbers, 71648, and we're going to input this into SOLIDWORKS. So let's create our porous media. I'll go to Flow Simulation, Tools, the Engineering Database, and I'll create our own new material. So I'll say new porous medium. We'll make this one unidirectional. Why unidirectional? The flow is forced to move in the x direction. It can't move up and down, and it can't move left and right through this plate. That's the way this porous media block has created the things for us. For porosity, we'll need to come back to that. Let me go to here, put in dependency on velocity, and type in the A and B that I just calculated from Excel. So 71648. And 983.24. Alright, now let's fill in the rest. So how do I determine porosity? So earlier I said that porosity was the volume of the fluid moving through my porous media over the volume of the block itself, the total volume of the block. So going back into SOLIDWORKS, we'll have to figure this out. Let me just put in a dummy number for now and open up my geometry. Using the evaluate mass properties, I'll be able to get the volume, the total volume with the porous media blocks, fluid blocks in here. So that's 11200. So I'll say 11200. Now the total fluid volume, if I didn't have all these cutouts in here, that would be 14080. So this is telling me that the porosity of my fluid volume is 20%. So 20% of the fluid will be flowing through that block. So I'll go ahead and type that into SOLIDWORKS, round it off just a bit. Oh, I grabbed the wrong number, 25600. Okay, I will be going with 0.96 porosity. Okay, coming in here. Unidirectional, dependency on velocity, got these two. Next to check is our calibration density. What's this about? The calibration density is going to be the density that you've tested your model at. So I tested this with water, so I should be putting in the density of water right here. If I don't put in a calibration density, every time I use this material, SOLIDWORKS is going to think that the fluid that I happen to be using in that test is the fluid that I did the lab testing with. So please never forget to put this checkbox in and put in the actual data here. So the density of water, that's going to be 997.6, about 1,000 kilograms per meter cubed. I'm not going to be doing any heat transfer, so I don't need to worry about this last box here. And this is all I need to do to create a porous media block. Now let's test it. I've created this exact same material with this here. We'll give this a test run. I'll save my changes with this porous media block. So I set this thickness to 0.018, set it up with the porous media that we created together, and I tested it for an inlet velocity of 1 meters per second. I did a back calculation here, so we should see an inlet pressure of about 102,600 pascals at the inlet face of that porous velocity. So when I ran this, it actually took me about 30 seconds. Not too bad. And I was able to find a pressure at the inlet face of this porous block to be about 102,625. So very, very close to what we predicted using the A and B constants with hand calculations. So you can see that this is really just pulling the data you put in your plot, but I'm able to half the time it takes me to calculate this analysis. Alright, so that is how to create your own porous media block that can represent real-life results in complex geometry. If you take the time to test and calibrate your data, you can save a lot of time during the simulation calculation. If we don't have any more questions, then this will be all for this webinar. Thank you for watching. This has been Shivani with GoEngineer.